C of Module 4. In this part, I want to give you a problem session. This is our problem session number 1. Yeah. So later we should have 2, 3, 4, depends on how many we need. Yeah. In this session, my plan, first, I want to go through all the questions from quiz 1 and quiz 2. After that, we have quite some time, probably 1/2 of the class I want to use to give you a few more examples targeting on your homework number 1. I believe there are some questions there, not very easy. Yeah. So I want to explain some of the questions. Also, I may find similar questions, different but type similar. So I solve a few questions like that. So just to give you some ideas how to solve those homework questions. Yeah. All right, so let's start. The first question, to evaluate a polynomial, the higher the degree it has, the more multiplications we need. We need to make sure if we say this statement is correct, it must be completely correct. There is no special case that it is wrong. So that's what I mean. Yeah. So here, when we make a statement, it must be 100% correct. You cannot find any counterexample. If you find one counterexample, it is wrong. Okay. So here we can find counterexample. So answer is false. The counterexample is we can find a polynomial with relatively high degree, but we do not need, the number of multiplications that is smaller than, that is higher than another polynomial with lower degree. Yeah. So that's easy. The counterexample we should find, the degree is power of 2. Power of 2. Yeah. Here, let me just use a simple example. X to the 4th power. Power of 2. Yeah. How many multiplications do we need to calculate this one? Power of, x to the 4th. Yeah. X times x. So that's one multiplication, right? All right. So after you get this number, x squared times x squared, another multiplication. So you just need 2 multiplications to get x to the 4th. But look at another example. a0 plus a1x plus a2x squared plus a cubed. Yeah, the general case. This one you can see the degree, the highest term, degree lower than x to the 4th. But when we use Horner's rule, we need 3 multiplications. Yeah. Because for the general case, we cannot use its special structure. For some special case, we may use special structure, but general case, how can you use the special structure? So we can only use that Horner's rule. Based on Horner's rule, the number of multiplications equals the number of the, what's that? The degree number, right? Yeah. Yeah. But 2 there, 3 here, that's the counterexample. Okay, yeah. So that is the first question. Second, when we solve some computing problem, sometimes it is a good idea to work on a few cases with small data sizes first. Then we can extend our solutions to the general case. True. In our problem solving, we use this strategy many, many times. It's a good strategy. It's a simple strategy, but very effective. When we work on some simple cases first, we can get experience. We need to use some experience to solve the general case of the problem. And we need to use some observation. So when we solve simple cases, we need to try to find some rule, try to observe some special properties. After we get those things, we can extend, we can generalize, to solve the general case of the problem. So that's the commonly used strategy. All right. Number 3, how many nanoseconds? 1 billionth, right? 9 zeros after 1, or 10 to the 9th power. So you just find appropriate expression. When I put an answer there, I need try to use all different possible ways I put there. So I hope, the hard thing is I cannot see your result. So I'm afraid if any of you, if you enter the answer that my options do not cover, then you couldn't get the points of this one. That's possible, but I do not know. So that's why for this quiz things, something, it's hard to give you partial credit. It's hard to give you partial credit. So that's the problem of the quizzes. All right. When you evaluate a polynomial, in order to get the best efficiency, which of following method should we use? The Horner's rule. Repeated squaring, that's for, that's for some special cases. Not as general as Horner's rule. Special cases. The special cases usually we refer to x to nth power. In that case, we can use that repeated squaring. But in those cases, we can do better, repeat squaring, better than Horner's rule. But that's mainly for this type, not the general type. Product rule, sum, not related, right? Product rule, sum rule, that's for the counting. Basic counting. In your discrete math, you learn these 2 rules when you do basic counting. All right. Question 5. This time we need to repeat it squaring. Power of 2. See? Power of 2. All right. How many multiplications? Minimum number of multiplications. So we keep doing that. X times x, so you need 1 multiplication, right? Repeated squaring, every time you do squaring, another squaring, 2 multiplications, right? X fourth, third, eighth, fourth, okay? So that's the total number of multiplications you need. This is the repeated squaring. Okay. All right. Next one. Since the linear search is too slow, yes, it is very slow. More specifically, that's slow. Okay, that's slow. Big O of n. it is basically useless to solve any real-world problems. Not useless. You cannot say useless. Yeah. The reason is sometimes we do not have better way to solve some problem in real world. Yeah, we have that situation. Yeah. So you are given an array of data, unordered array. How about that? If you have unordered data, what you can do? You do not have many ways to do the search. In that situation, the only way you can do linear search, right? Yeah, it is slow, but there is no better solution. So we have to take it. Yeah. So we cannot say it is useless. Okay. Yeah. False. Yeah. All right. Number 7. Given a computing problem, if you have an algorithm to solve it and you cannot improve it anymore, then you can say that an algorithm is optimal. Check your understanding on this optimality of the algorithms. Answer is false. So I hope you can understand this one a little deeper, yeah, because the reason you cannot say it is optimal. There are several ways you can view this. Yeah. You cannot improve it anymore. That's about you, right? You do not have the capability to improve it. It does not mean other people cannot improve it, right? Other people can still have chance to improve it. If other people can improve it, then it is not optimal, right? Your algorithm is not optimal. Yeah. So that's one view. So other people can do it. All right. Then go to another level. Nobody can improve it. Can we say nobody? If nobody can improve it, can we say it is optimal? Still no. We cannot say that. Even nobody can improve it. Can you exhaust everyone in the world? Right? Nobody improve, nobody around you, right? Nobody in some community, right? Can you exhaust everyone in the world? Even you can exhaust everyone on earth. Can you imagine there is some creature in different planet? They can do it, right? So there are all different possibilities. You cannot completely eliminate them. How can you say nobody can improve it? Even, yeah, let's just talk about people on Earth. How do you know? Even if nobody can improve in the current world, how do you know after 3-5 generations someone can improve it? Right? After several generations, people can improve it. Then your algorithm is not optimal. Right? Yeah. So from that understanding, you cannot say that. In order to show your algorithm is optimal, you have to show nobody can improve, no matter what, no matter how many generations, no matter who, where in the world, even other planet, no matter what. So nobody can improve it. Yeah, that's possible. We can show that. We use the logic. We can show that. Okay, so if you can show that, then it is optimal. Okay, yeah. So that's the meaning of optimality. Yeah. All right. Number 8. Given an array of integers, to find the minimum of this array, the best way is to sort the array first. After that, not the best way, right? Yeah. Because when you sort it, you already spend a lot of time, a lot of comparisons. Yeah, not just time. Too many number of comparisons. And find a minimum, we don't need that many. Yeah. So that's definitely not the best. It is a really bad way to do it. Very bad. You should not do it in that way. Yeah. False. Okay. Yeah. Next one. Given an array with 12 elements, we sort it by the selection sort. How many comparisons do we need for the average case efficiency? Yeah. This one, when we discuss this selection sort, I ask you that question. So worst case, best case, average case. Yeah. Probably I give you the answer. Yeah. I mentioned a little bit. Yeah. I couldn't remember clearly. Yeah. But the answer is all those cases the same. Best, worst, average, all the same. Yeah. So in that case, only one choice, only one answer. Yeah. You just find that answer. Okay? Yeah. The reason I ask you this, I try to confuse you a little bit. Yeah. Because when you see something not quite familiar with, so you may not feel, very confident. Yeah. So in that kind of psychology, you may give the wrong answer. Yeah. So that sometimes when I design questions, I may use that way. Yeah. This is one example. Yeah. To find answer, we have the formula. You just use that formula. Okay. Yeah. So 1/2. Yeah. So you just recall, right? From, n times n minus 1, right? Yeah. Comparison. From 1 plus 2, yeah, 1 plus 2 plus the last one, n minus 1. That number. So you can use this formula, okay? So you plug in 12, 11, 66. That's the answer. Yeah. Last question. Question number 10. Given an array with 100 elements, we want to do the linear search on this array. It is known probability key appear in the array 0.8. Yeah. What is the average number of comparisons to get the search result? Yeah. We have that formula, right? So we have that formula. All right. 0.8%, not percent, 0.8 chance probability in the array. Right. 0.2 chance not in the array. Okay, yeah. So you need to find the average. For this case, what is the average? Yeah, the average of 1 plus 2 plus n over n. Okay, what is the average? N. Okay, so then you find that number. Okay, 0.8 times 1/2 n plus 1 plus 0.2 n. Okay, so you calculate that answer. N is 100. Yeah. All right. Yeah, 100. So 0.4, 140, 40 times 101. Okay, so that's 120, right? Yeah. Not 40. Yeah. 0.4, 40, 101. 4, 1040. Oh, sorry. Sorry. Yeah. Okay, yeah. Because after I need to divide it by n. So after divided by n plus 1, right? Yeah. So 0.4 times 101 plus 20. Okay, yeah. 40.4 plus 20. 60.4. That's the answer. Yeah. That's the answer. Yeah. I forgot to do this division. So that is this. Yeah, but in our formula, if you go to the notes, you just directly use that formula. So it should be correct. Yeah. Yeah, because for some relatively simple formula, I do not try to memorize it. I just derive it. Yeah. But sometimes I make mistake here. Yeah. Anyway, yeah, because the number looks ridiculous. Yeah. Now it looks right. Yeah. All right, so that's the part C.1 for quiz 1. Yeah. Next part we will do quiz 2.